Haskell is a pretty unique language because it's not the new features that it offers that makes it special, but that it offers a completely new way of logic. And this is something that I would recommend people to at least know about and try once because its principles could be applied to other languages to produce some shockingly elegant and simple code. Okay, so here we have the Haskell interpreter. It's like an interactive prompting as you would see in like Python or Node.js. So let's just start with a fact. All variables are constant. What you would think as of a variable, for example, like x equals to 3, is constant. You can never change that at all. And that really isn't like a restriction, but you can more think of it as just a way that the language works. It wouldn't make sense to define this in another way. If you did change it, that's basically redundant and there is no meaning. Because for Haskell, you can also even abandon the idea that files are stuff that start from the top and have each instruction at the bottom. Because for our typical languages, we do stuff based on statements. But for Haskell, everything is an expression. You can write functions and you can define variables, and that's basically it. If you're running it in a file, only one main function could be run, and everything else is just essentially you can think of it as helper functions. So let's just start with something that's pretty simple. Let's say we want to write a function. Instead of as normal programming languages where a function is kind of like a block of code, everything is in fact an expression, and so are functions. So all they are is, for example, you can write f of x kind of like mathematics, except you don't have parentheses. You just say f x is x times 2. And there you have defined a function like that. So now you have defined it, you can just simply call it by saying something like x f12, and that will give you 24. F, for example, 0, that will give you 0. F 200, that will give you 400. As you can see, it's kind of like any other language. But the key part to notice is that these functions are what we call pure. So they are deterministic. They do not access nor modify any sort of outside data. So whenever you give it the number 200, as you can see logically, it will always give you 400 and nothing else. The great advantage of this is that by declaring functions to be something that is to be calculated or to be expressed rather than something to be done, you can much easily test something. Because if you were to test a function but you had to set up, for example, your app in just the correct way, or else it might have a chance of crashing, that's very hard to test. But with these functions, if you give it a number and it gives you the number you expect, you know it works. Okay, so those are functions. And this is really similar to what we would expect, for example, as an arrow function in JavaScript. So let's say we run a Node.js, we can just say something like let f equals to x arrow function x times 2. And something like this gives you like similar results. And given the nature of Haskell, it gives you a wide array of stuff. So let's say we want to make a word count option. All we can say is, for example, count string equals to length of what? Length word string. And now we have that done, we can just say something like count the quick brown fox jumped over the lazy dog. Let's just write a sentence like that. And then it will give us 9 for each of the 9 words in the sentence. What this does is basically the word split string into a list of smaller strings for each word as it spaces, and then length just gets the length of that list. So these are really the main things that functions do. They're simply an expression that you can evaluate. Okay, now we're back in JavaScript just to show you a quick thing. So let's say we have a function that I have already wrote called add, and we can just add 2 numbers by passing in a number like that, right? We can say add 5, I don't know, 10, and it will give us 15, like that. Very simple. But if we only pass it in like a variable called 5, this will fail, and for obvious reasons, because we haven't produced like enough parameters to give to the function. But what if I show you an alternative to this function? And now we have the function other add, and you can see what it does. So we have 1 and then 2, like that. We have 2 parentheses this time. We can give it 1, 6, like that, or maybe let's say 10, and it will give us 16. So how is this done? This is actually default stock JavaScript. Let's look at this a little bit clearly. First, we only have the function other add, which takes the number 10. So how are we calling it again? Well, the simple answer is that we basically create this function when called that takes only 1 input, but it returns a new function that also takes 1 input. Therefore, you kind of divide it into 2 functions, and you can only apply part of it. We can say something like let add 5 equals to my other add, so we can just say 5, and that's it. Now we can call it add 5, and so we call 10, and it adds 15. If we call 1, it gets 6. So you can apply part of the function, and this is called partial functions. And the way we had done this is very easy, simple. So let's say we write my add, right? This is simply x, but this time you only pass in x, and then you do another one. And here you do x plus y. And this double arrow may feel like some unfamiliar syntax, but if you look at it closely, let me add some more parentheses, you can see very clearly what is happening. You're simply having one function that returns this, another function which also takes a value. And then because the value from x is stored from the outside function, you can then use those two if you use two parameters. In Haskell, this is actually the default. So let's take a look at this. To write the same with two parameters, we simply need to say add x, y equals to x plus y. And now we have that. So we can say add 1, 2, and then it gives the correct answer. But we can also say, for example, add 5 equals to add 5, like that. And now we can just call add 5 as any number we want, and it would do the same thing. So this method of partial application of functions is actually really, really useful. So for example, the syntax would be a little bit unfamiliar, but we have the map function, which basically loops over a list. It goes over a list and then applies a function to every one of the values. So we can say map add 5 here, and then say 1, 2, 3, 4, 5. And for each of these, you get 6, 7, 8, 9, 10. And all you had to do is just give one of the parameters the add, so that instead of add being a 2-parameter function, it becomes a 1-parameter function that can be applied to numbers. And in fact, it was never a 2-parameter function. All functions in Haskell is basically essentially 1 parameter. So there's a command for getting the type of something, and we can say type. Let's first look at add 5 to understand what it does. So this part you can ignore, that's just a name that just signifies type. And num_a just means that this is a type where it has to be a number. But here's what we need to look at. So we have a to a, which means that a type of a number to another number. And that's exactly what addition does. All right, you would assume something like for add, the add function, it would be like add a 2 variables to 1, right? But that's not actually how it works. So let's look at type of add. And you can see it's a to a to a. So just as a JavaScript example, if it makes this clearer, we can add some parentheses. So first is a one function with one input, right? A, which gives you another function that also takes another number and gives you a final number. And that's how you basically have functions with multiple variables in Haskell. So partial functions aren't just for convenience, but also a pretty key part of the language itself. So for example, instead of saying map add 5, we can say something like map add. What will happen is that this is perfectly valid, despite the fact that it accepts technically what we see as 2 parameters. Because this time, it's just that instead of returning a list of numbers, it will return a list of functions. And if we press enter, it will show something like an error, but that's only because it doesn't know how to show a list of functions. But this expression is perfectly valid, and we can use it later on. And that's the key part about functions. They're all the same shape, except that some functions return other functions instead of returning a value directly. Let's say we write another very easy function like, I don't know, test fx equals to fx. And what this does is that it accepts a thing called f, and we just call it f because to signify it's a function. And then we pass it in a value. And then we actually call the function we just passed in with the value that we also passed in. So just to add the example, we can say something like test add 5, 10, and this will give us 15 because f is add 5, 10 is x, add 5, 10 would be 15. However, we can also say test add 1, 2, even though it wasn't made for it. It technically only accepts the value 1. So what happens to the 2? How does it also work? That's because this expression gets evaluated first. This entire thing is equivalent to calling add 1. But add 1 itself evaluates not to a value, but another function. 2 can also be passed into it. Therefore, we get the final result of 3, despite not making the test function initially seeming to fit output with 3 numbers. So you might be looking at this and wondering how Haskell can calculate basically anything other than just pure math functions. After all, everything you seem to look at has to involve state. Like, for example, if you're coding a video game, you're coding a web app or anything, if you don't keep track of what's happening, how are you supposed to do anything with it? Well, that's the problem with our chain of logic, right? We tend to think of state as like a data that you keep there, and then all of the functions access and change. However, in Haskell, there's actually ways to get around this. Let's say we have a video game, right, with a universe with objects in the player. So we can say something like, instead of saying, for example, world equals to create world, player equals to create player, player dot move upwards, you can simply say something like create player, right, first of all, and that returns the player. And then what you do is that you have a function that wraps around it that says, for example, move up, and that accepts create player, like that. And then you can, of course, this isn't actual Haskell code, you won't have parentheses and anything else. And then you have another one that's like, I don't know, take damage, and that you wrap it around. So each time the value of the player is actually moved from one function to the other function. And you can see that data can flow this way as well without ever changing the initial player that was created, so that none of the functions that, for example, are referencing the original player would ever get affected by anything else. Okay, so admittedly, you are probably not very satisfied by this. This seems like terrible code to just wrap them in parentheses and parentheses and parentheses, and plus, functions don't have side effects. And think about what that means. They can't modify anything outside. By displaying a number on your screen, you're modifying the pixels on your screen, therefore modifying the information that goes into your eye, therefore modifying the information your brain is thinking about. That's not allowed in Haskell. So the answer to this situation is that you cannot have all pure functions, because then you can't have any input or output. So the solution is the creation of a new type called IO, which all functions that interact with the outside world must return. Therefore, functions that don't accept this type are not able to be used along with these functions, because it would simply result in a type error. Now, using this method, it is able to be separated out from all of the pure functions. But before we get into that, let's take a brief detour into the complicated subject of monads. Okay, let us actually look at something a bit more theoretically and just the logic of how stuff works. So first of all, if you have a function that relies on the output of another function, so you pass one into the other, you can also write it in a way that basically makes it easier to read. Instead of one inside the other, you can just say like one to the value of the other. So you can write something like g of x and then to f and then to something else. And or you can rather say x to g, basically just passing values around to each one function to another function. And I'm just going to use this syntax, and in Haskell there's actually an operator that kind of does the same thing, and we can talk, and if you want you can look into that further. So for types, of course, you can have stuff like numbers, you can have strings and everything else. So let's say we are making like a linked list, or if you don't know what that is, just think of like a bunch of trains. Maybe the trains have a property that's like train, like the car dot previous, right? So it will give you the previous segment or the next one. But sometimes it might be nothing if it's the end of the list. What in most languages would be something like no or undefined or something like that, but Haskell doesn't. So here's where we introduce the type maybe. So for maybe, right? For maybe, you can have two types. It could be just, for example, just the number. Let's say we're dealing with numbers. It could be just 5, or it could also be nothing. That's the two types it could have. You can write a function like get prev, and then you need to pass it in like the current car is the current train, and then it will return you, like, for example, either just the train or nothing if it doesn't exist. That's very simple. But maybe you want to get it twice. Maybe you want to get two segments above. Well, how do you do that? Like a logical way of thinking about it would be like get previous, right? Get previous, and then train. But this wouldn't work, and maybe you can see why maybe you can't, because the reason is that the input to get previous is simply train, right? The input to get previous, you simply give it a train, but the return output is maybe, and then it's maybe train, something like that. And here's the problem. You can't pass maybe train as the input. It has to be 100%, like you know where it is. So now we are right out of the problem. But like one way to solve it would be like we use something called case, or like if statement. It's like if it is actually a value, do this, like actually calculate it, or else if it's nothing, just simply do nothing again. And this works, But you can see how it becomes really tedious if you were to have multiple functions that you just want to simply chain together. However, you can't. And now where's like our clever part about basically monads come in. So monad, all it does is like a special operator. So instead of passing your value directly into the function, you pass both the function and your value into another function that deals with how it's supposed to be done, like how the value is supposed to be given to the fed into the function. So for maybe, we can write our custom function that's very simple. We can just like say if it is like just like x, then just say like call like f x like that, or like maybe like else, just like return nothing, or just say like else is nothing. Of course, this is in Haskell. You can't run this, but just as an example, and this basically does what we want. So let's say we define it as using like something like a double arrow, right? So we can just simply now say train, but we had to create it as before as just the function, right? We had to make it into the type, so it has to be just train, like, or simply a train into, and then we can give it a value to that function. So like get previous, right? Get previous, and this essentially does what we want because it takes just train and just it separates out the value here and passes it into this, which returns the maybe, and then which just simply separates that out again and passes it into that. Or if it's nothing, we can simply basically skip it and simply return nothing, which you can go into this function and chain together however you would want. So just to give an example of another monad, maybe we can say we give a function called increase, which increases x and basically just gives it x plus 1. But however, like, we cannot use console.log in this world. So what if we say something like that simply just passes another string along as a log result? So we can just say, maybe we can say increase x. We can use something called a tuple, which is just like a pair of values. We can say the first value is your actual result, but the second value is like maybe like wow, big number or something like that, right? Something like that. And just to standardize it, we can maybe call this tuple like a type of something that's like log, right? You have the actual value and part, and then you have the log part. So now what you do, let's say you have another function called multiply, or maybe like square, actually, just to keep it simple, have one function. Let's say we have a function called square x, and it does the same thing, x times x, and then it has like hello or something as a log, right? Say you want that. But now we have the problem, like if we have 3, we want to make it so that you increase it by something, and then you square it, so it's 4, and then you square it to get 16. This, as we said before, this will not work because it wants a variable x, but you're actually passing in a tuple that has both x and hello. So of course you could rewrite your functions to do something that doesn't require this. You can rewrite your functions to maybe only takes the front part. It's like x, the 0th index or something. But that would be a hassle to do, and it's quite annoying, right? So now we can make a function that's like the arrow function be set equals to like if you have f. Of course, I don't know why I use this notation. It might be confusing. It might be not. The actual notation is this. So bracket equals to. But the point is, what you can say is that you take the value, right? You take the log, which has both the value and the text, and you separate it out. So you separate this thing, and then you actually pass it into the square function here, and then you add back some message. So you have this part, or maybe you want to add the previous person's message as well. So now with this message, you can pass it along happily down the chain. And you can say that we have here, we use the same for log just to as like a comment. What we can also do is emulate state by having a variable that gets passed along all of the expressions, but it just maintains the same value, or you can optionally choose to change it or differentiate with it. You can see that we can start from value, we can change it, we can choose to mutate it however we want. Okay, so now we turn back to the real problem of reading and writing user input. So these functions are what we will obviously call unpure. So I'm just going to impure. So I'm just going to first tell you that there's a function called print and there's a function called getLine. Print just prints a value. GetLine simply gets a line that's inputted from the user. So let's see how this is done. Basically, as I have said, Haskell, you cannot try to, for example, pass in a function that expects an int, a string, that will just immediately file. And also with the maybe thing, we cannot pass in something that is part of a maybe, like wrapper, when the function is simply expecting the inner value. So the creative thing is that instead of getLine being something that returns a string, it actually returns a new type called IO string. And what this does is that if you try to pass it in, for example, let's say use our count method, right? If you say count get line, this will fail. It will say something like expected type string, but instead got IO string, so that you cannot mix and match these. And this highly encourages the facts of using pure functions and only using these to get them, separating out so that your logic is very easy to organize. But you might think, what's the point of writing normal functions in if they can't interact with each other? Don't you have to write all functions to accept the IO string? And that's where the monads come along. So you can start with a function that's like getLine, right? And I'm not going to use the arrow thing because that's misleading. I'm going to use the actual thing, which is this, right? GetLine, that value gets passed into a function, let's say count. And this does exactly as we said before. You can implement a custom method for each of these monads and say define that in this case, what this arrow does is basically take the IO out of the string and takes the inside value actually, and pass that into count because count expects a normal string, and that gives out your output. The fact that count returns an int isn't the problem. The problem is that the count function returns a normal int, not an IO int. So this means that for monads, it's required that each of the steps have the same type on the outside, the same type IO. But it can change from, for example, an IO string into an IO int. That's perfectly acceptable. If you want to do another operator and chain this along, if it's in IO, then there's no point of doing this, right? To convert an int into an IO int, they offer a function called return. And that's just a normal function. It's not a keyword. It's very misleading due to the name of it. But all it does is that if you give it in an int, and also the outside, context of this is that we're using IO, then it simply changes int into an IO int. That's all it does. But we can't exactly wrap it around count like this, return count, because we still had to pass in the variable, the value here into count. So we can't just return it directly because that would be just returning the count function. So it won't be IO int, but simply IO string function. Like it's going to be like a function which is like not correct, right? So to solve this problem, what we can do is write another helper function that's like combine, right? Let's just do that first of all. You have the first f, and then you have a second function, and then you have the actual value here. So what you can do is call essentially f of g of x like that. This is of course also not real Haskell, just to make this a little bit easier sounding. And then what we can do here is basically write, instead of count, we write combine return and count. And we can omit the x because of partial functions, so you can simply, this itself would be a function that works in this case. And actually we don't need to write our own function in this time because Haskell, because we use it so often, this is a default, we simply write return dot count with a space in between, because this is actually a function, just uses a special name, and it does exactly the same thing as combine, except we write it in the middle. But now we have that. What we can do is now it returns the IO int. Maybe we want to print it, right? What we can do is just add another one. We just chain this along, and then we write print right here. Because the IO int accepts a regular value, so it takes int, puts it into print, and print actually returns the IO nothing, written like this, right? Two parentheses mean nothing, because print doesn't need a value to be returned, but it still has the IO property. And that could be our end of the expression. Okay, so let's look at the function getLine. So you can call it just simply like this without no parameters, and you can say hello, and it will give you the string hello. But let's check the type. So let's check the type, not hello, let's check the type of getLine, and you can see it's an IO string. For example, if we had our original count function, it will give you an error, like expected string but got IO string. Now let's look at another function, print. And print does what you expect. Print hello gives you hello. So we have print. Let's check the type of print. Type print. It says you have show a, but basically it's like anything that could be shown, so it's not just a string, but we can ignore this and basically say a string is an IO nothing. This doesn't mean like you're calling IO or anything. This just simply means nothing because like print doesn't return a value of any type. Cool. However, we can't say print getLine as you might have expected because it's expecting a normal value. So what you can actually do is use that operator I was talking about, and then you say print. So now you can say, well, you can't delete, but you can say this, and then it will just give you that. And if you're confused on what's happening, basically you're taking the IO string, you're ripping the string value out of it, you're passing that into print, which can print that and then prints it out. And then you can type kind of like pass this back out along because this returns the IO string, so that's a valid return value. So finally, just to show the example we have done before, what we can do is start with getLine, and then we pass it on to count, but of course we have to wrap count with basically return, so we do that. And then we can say maybe do the same thing again, return word, return square, and then finally we print it. And all of this works very nicely. So we can say the quick brown fox jumped over the lazy dog, so it should give 9 and then square it, so it will give you 81. And as you can see, this is the true power of Monads. You can chain together these for as many as you want, and then you don't have to deal with the messy format of having to wrap functions outside one another. And with this, with just one type Monads, you can use it for many different types and uses. For example, we can use it for IO and also use it for maybe, which we also showed before. So there's no need for special syntax for optional chaining, special syntax for, messing with impure functions, or any special syntax with stuff I haven't mentioned in a very elegant and expressive way. And that's all for this video about Haskell, or really a video about functions itself. What I hope you have realized is that functions aren't just simply a shortcut to run a group of code, but could be so much more powerful and made into the fundamental structure and building blocks of the way we think and tackle problems.